Hey, Colin, feel free to ask me questions if you have them. I'm just prepping for class.
Uh, I guess the only question I was wondering about is chapter 10 going to be the last chapter we cover? Because I was looking through the modules and originally it seemed like we had like 13, but now it looks like 10's the last one.
No, we actually have a chapter 11 that ideally we'd start it today, but I don't think we're going to be able to get to. And then we want to do 14 and 15. That's the ideal scenario, but I do the 14 and 15 kind of short.
Yeah, and I was also just wondering, what is the class schedule again for next week with Thanksgiving?
I think, or let me double check my schedule here. But I think the school's only closed on Thursday and Friday, so that means we get our full schedule for our class, but I'm not positive. Let me double check to make sure.
Yeah, it feels like with the Wednesday class, I have a feeling a lot of people are going to be missing.
Yeah, that's normally what happens. The good news is I usually don't make it critical that you're there, but I usually do cover material so as to not waste it. But let's see. Thanksgiving holiday begins on November 26th. Today's the 17th. The 26th is, oh, it's Wednesday, so they actually
Wednesday.
have Wednesday off. So we'll just have Monday of next week. And
Okay.
then, if I remember correctly, the last day of classes is December 12th. That's for exams and everything. So, yeah, that seems about right. That still gives me all of the following week and stuff like that. So, yeah.
Okay, and both the final face to face and the final it's like the third face to face and the final itself are due by the 12th
Yeah,
or the
usually
6th?
the final face-to-face would be the week before, and then the final
So the
exam will be the,
6th.
the very week of, exactly.
Okay. And we have to schedule the final or is there like an actual time for that?
No, you can schedule it. I give you like the same normal 6 or 7 day period to do it.
Okay.
Yep.
All right.
If you need it
Cool.
earlier, I can usually accommodate that too, because sometimes I have students going away for trips. Other times they're going to another college or something like that. So if you need it to do earlier, that can be arranged as well.
Okay. Will chapter 10 take just to for the rest of today, or will also take Wednesday as well? Just because going through 10's like so far with the homework and like just going over like the study or the with the studying for uh
Next test.
the quiz,
Uh-huh.
uh 10 is a lot more complicated than 9. We
Yeah,
spent like 2 solid weeks on 9.
Yeah, yeah, 10, we're gonna finish it up tonight, even though, well, I assume I will. I have like 5 examples I want to make sure I get. If I get them, then we shouldn't have any problem. 11 goes really fast. I shorten that. 15, 14, and 15 go really fast as well.
Okay. And no 12 or 13?
Nope, nope. I usually make those homeworks available so you can learn them if you want, and I give you extra credit for it, but you're not required to.
Okay. Um, all right. And for the test, you said like since the 9 to 10 test is only 4 questions, but it's is the scores on that like doubled? Just because, at least for the practice, it's still like 4 questions, but it's treating it like it's 8. So even if you get everything correct, it's only a 50 out of 100.
Yeah, I thought I corrected that last week and sent an email and everything. Let me double check that now
At
because
least
that's a problem.
for the practice, it's still the same. I don't know about the official.
Yeah, let's see here. I'm glad you inquired about that because I swore I fixed it. The actual online test is what you had taken, right? You're the one that actually took it and got a.
No,
Uh,
no, no. That was someone else. I was just
okay,
doing the
gotcha.
practice last night, and it was still the same issue.
Oh, okay. So yeah, that's definitely an issue. I'm checking this one right now. See what's going on here. There's missing questions in the online test as well, so that stinks. Yep, I fixed it and it's not uploaded, so evidently I fixed it and then it didn't take it. So I guess I'll be fixing that tonight right afterwards. But yeah, and like I said, the student ended up getting like 60 out of 60 because that's the only number of points that was available. So that's 100 in the bank for them. But really, anybody that took that, I want to make sure they retake it so they can get the full breadth of it, even if their grade's still 100, just because you need the experience with the other
Yeah.
questions.
Okay.
So sorry
All
about
right.
that.
No, it's cool. I'm just bringing up as like, oh, might be an issue. Okay.
Yeah, yeah, that's an important one. I'm glad you brought it up.
Okay. All right. Thank you.
Thanks. Aiden, feel free to ask questions if you want. Only got couple more minutes. Y'all can also go ahead and chat me your first and last name if you'd like.
Yeah, so
Yes.
I was talking to a fellow student about the online test that,
Mm-hmm. Uh, you just went
like
blank.
the
Oh, there you go.
sorry.
No problem. I can hear you now.
Okay, yeah. It went from 65 out of 100 if you even if you got 100 on it, so I just wanted to make sure that that was being fixed.
Yeah, I fixed it Friday, and a student just let me know that evidently that did not fix it. So,
Yeah, I
uh,
took it yesterday night and I got a 65.
yeah, I'm refixing it again because what I did was I fixed it, posted it, but now I see that it's not showing again. So I'm in the process of making another one. In other words, if you've got 100 on it, you don't quote unquote have to do it again, and you automatically scored your 100. So if you got 60 points out of 60 or 52 points out of 52, whatever it is for both the practice test as well as for the online test, then that's your score. You're going to get 100, but I really want to make sure you take it at least once so you can see the questions that you missed because you missed basically a lot of questions from other chapters that will be on the actual test.
Okay.
Okay.
Um,
The one that was bad now has an asterisk on the name, and I'll be putting the word bad in the name in the title. And right now the good one will just say the regular PTO6 and OTO6. I just finished fixing the practice one, and I'm getting ready to post that now for you.
okay, thank you.
No problem.
And then I also remember reading in the syllabus too that there is extra credit exams. Does that include the online test as well, or is it just face to face?
There's extra credit. You blanked out a little bit, so all I heard was there is extra credit, and then there was no noise, and then you started talking again. So I don't know what you mean by extra credit, but there is extra credit for taking the practice test, if that's what you're asking about.
Yes, that was I was referring to, was it just the face to face or for the online and the face to face?
You know, definitely online and face to face. So basically, what happens is at the end of the semester, I take your highest score on each of the practice tests. Hopefully, that's 100. And I average that, and then I divide that score by 20. And for instance, if you had all hundreds and you didn't miss any of them, then that means you've got a 100 average. You divide that by 20, that gives you five. And that's literally 5 points that goes on your final exam.
Okay, so that's on the final exam. That's not 5 points to either numerical
Yeah, if
grade.
I
Okay.
think whatever the syllabus says, and I'm pretty sure it said on the final exam. But if it said otherwise, then I have to honor it. But I was pretty confident it said on the final exam. Hopefully,
Okay. Thank you.
you're welcome. Everybody, feel free to go ahead and chat me your first and last name. We still got another minute or so before class starts, and I just finished fixing PT06, chapter 9 and 10. You can tell the old one will have, right now it has an asterisk in the title, but I'm going to put the word bad in it so you'll know. I just did that. And now I'm going to do the same thing for the online test, but I'll be fixing that tonight as well. All right, so I guess we should go ahead and get started. Let me make sure I've got all this undone down here. Remove that. That's good. All right, so I want to let you guys know, for starters, it's time for class to start, so you can go ahead and chat me your first and last name. So I have that for roll. And I'm attempting to finish up chapter. I'm attempting to finish up chapter 10 tonight. That's going to involve some specific examples. But a student asked last time and earlier today as well, asked about the online test 6, which covers chapters 9 and 10. But of course, always my tests are comprehensive, so it covers 1 through 10 basically. But actually, I called that online test 6. It was online test 5. Sorry about that. It's the practice test 6, though. So both the practice test PTO 6 and the online test OT 05 had a problem. Basically, one of the banks of questions wasn't working, so there are an incomplete number of problems. Uh, the same thing was true with the actual test. So I've put the word BAD and then an asterisk in front of the name of the online test, as well as in front of the name on the practice test. And now there's a new one with the same name, except it doesn't have the bad word and it doesn't have the asterisk. I want you guys to do those. If you've already scored 100, you're going to get 100 no matter what you score. But I want to make sure you guys all take that practice test a couple times, as well as the online test at least once, so that you can get a feel for what the test will be like. Because those versions that came up missed some key questions that were, mostly from chapters other than 9 and 10. But I wanted you to get a full feel for what it's like. So the practice one's already up and corrected. And tonight, right after I get offline, I'll be fixing the online test. And if anybody needs to extend the date, I'll do that. It's not a big deal, but I'm going to keep it as the 22nd until right now. But it shouldn't be a problem. If anybody needs me to go ahead and move it to the 23rd or even the 24th, I'd be okay with that. So just let me know if you want it. But hopefully, you all can get it. Does anybody have any other questions before I get started on chapter 10 stuff? All right, well, we're going to start off with example 1010 from your textbook, and I'm going to start by sharing my screen. So let's do that. It's coming up any minute now. Okay, so now you're looking at the drawing for example 1010. Let me go ahead and read the problem to you. This is another one of those times where I'm using the examples from the book, so if you actually have the e-copy of your book open, that'll be more helpful to you. So it says a heavy pulley, a 15 Newton force represented by Ft, and I use the same symbol here, is applied to a cord wrapped around a pulley of mass 4.00 kilograms and radius R0 equals 33.0 centimeters. The pulley accelerates uniformly from rest to an angular speed of 30.0 radians per second in 3 seconds. Assume there is a frictional torque sub friction equals 1.10 meters times newtons at the axle. Determine the moment of inertia of the pulley rotating about its center. So this is a case where if I use the center axis of this pulley as my axis of rotation, then that's a fixed axis in a non-accelerating reference frame. So we're allowed to use the equivalent version of Newton's second law. That means we're going to use the summation of the torques is equal to I times alpha. That can be written as a vector slash pseudo vector equation, but that's what we're going to use. And all I have to do now is take that and figure out what the net torque is. We see that we have one torque, the Ft, is tending to rotate this pulley counterclockwise. I'm going to call the counterclockwise direction positive like I normally do. And then we have the friction torque that's tending to rotate it in a clockwise fashion. So I'll call that negative. So now we're going to get the following solution. The summation torques is equal to I times alpha. In this case, I'm going to get 15.0 newtons times 0.330 meters. Notice how I did convert that to meters. Notice also that it's positive. And since the force is actually perpendicular to the radial line, then that means that the torque is just force times the radius in this case. So that's what I just drew that blue radial line there for. Now I'm erasing it. So that's why it's just 15 times 0.33. And then I'm subtracting from that 1.10 Newton meter. Your book is using meter newtons because it doesn't look as obvious like a Newton meter, which makes people think of joules. But at the same time, it looks just like a millinewton. So that's a whole nother problem. What we have to do is set that equal to I, which is what we're trying to find, times alpha. So I need to figure out what alpha is. And what we have is a alpha that we can get based on the omega zero and omega final and delta t. Specifically, alpha is equal to omega final minus omega zero over delta t, which is 30.0 radians per second minus 0 over 3.00 seconds, which equals 10.0 radians per second. So now all I got to do is put that alpha in right here. And I'll just leave the units off. Well, actually, no, I can fit that unit in. I just need to erase this a little bit. So that's 10.0 radians per second. And that allows us to solve for I. So I is going to be equal to 15 times 0.33 gives me 4.95. So this is going to be 4.95 Newton meters minus 1.10 Newton meters. All that divided by 10.0 radians per second. And 4.95 minus 1.1 gives me 3.85. So this is, in fact, divided by 10 is 0.3850 kilograms times meters squared is I. So that's our moment of inertia for this pulley. Anybody have any questions on that one? Now, as the problem methodology that the textbook is teaching you says, when you're finished, you should apply Newton's, or excuse me, you should solve for unknowns and then do a rough estimate to see if the problem's reasonable. In this case, a pulley sort of looks like a cylinder, so we might be think be thinking that the moment of inertia should be roughly equal to the moment of inertia for a cylinder. For a cylinder, I derived that last time, it's 1/2 mr squared. So if I took zero point 0.5 times 4 kilograms times 0.33 squared, I would get 0.2178 for my moment of inertia. And in our case, we got 0.385 instead of 0.2178. But that's at least the same order of magnitude. So I would say that's not a bad estimate. Okay. Now we're going to go ahead and try what looks like a very similar example, but slightly different. So let's look at example 1011. So here's example. Whoa, no. Here's example 10-11. And this one says, consider again the pulley in example 1010, but instead of a constant 50 Newton force being exerted on the cord, we now have a bucket of weight 15.0 newtons, mass equals 1.53 kilograms, hanging from the cord. See figure 1023A. We assume the cord has negligible mass and does not stretch or slip on the pulley. Calculate the angular acceleration. uh, they're saying A there, but that should really be alpha of the pulley, and the linear acceleration A of the bucket. Assume the same frictional torque. Torque friction equals 1.10 meter newtons acts on the pulley. So we have more or less the same diagram, except this time the force is going to stay. Uh, Instead of being a constant 15 newtons, it's going to be a 15 newton mass hanging, or a 15 newton weight hanging, if you will. And when it's hanging, as it starts to accelerate downward, that's going to make it a smaller force than the 15 newtons. So it's slightly different because of that. So let me start by trying to draw a little bit of a figure here. I'm going to try to make it a circle, and I'm going to try to draw it as neatly as possible. So I'm going to use the little tools that this program has to make it nicer. Whoa, no, that was not a good idea. Something bad happened on that one. Whew, that was rough. Okay. So something like that. We still have that torque going around this way. That is the friction. This time we have instead a tension T, and I'm just going to call it T. I don't like doing a subscript F with a subscript T on it. We still have the same radius, so we still have R0. We still have M, where M is 4.00 kilograms. R is 0.330 meters. And we still have the acceleration alpha was equal to 10 point. Well, we can't say that now, so I'll go ahead and leave that one off. In this case, they're actually asking us to determine alpha. So in order to do this, I need not only that free body diagram, which I have, and using the summation, I should probably switch to green again. Let's go ahead and put that number back here. That's still meters. But now we have solution. The summation of the torques is equal to I times alpha again. I instinctively write the vector symbols just so you get used to writing that and being careful about such things. But again, this is just one,
Um,
more or less one dimensional because we're looking at rotation. But we will,
Professor,
yes.
why is the M in the on the pulley there? I thought the mass was supposed to be the bucket.
Oh no, no, the bucket is what's hanging from it. So the mass that they gave us was the mass of the bucket, and that was the 1.53 kilograms. So we would write that, for instance, as little m is equal to 1.53
So the 4
kilograms.
kilograms is the pulley itself then.
Exactly.
Okay.
Good question. Okay, so we have this, but now we also have this other diagram. Now, notice I've sort of made the assumption that counterclockwise rotation is positive. That's what I did previously. I'm going to do the same thing, and to not have to randomly stick negatives in there, like in the equation for rolling without slipping or something like that, then you try to make all that consistent. So, what I'm going to do is draw an additional mass which shall be this little quantity right here. That's M equals 1.53 kilograms. And we have acting on that in the positive Y direction. Okay. We have acting on that a weight W equals 10.0 newtons. But we also have acting on that in the opposite direction, the same tension that we had above. So from this free body diagram, the circular one, From that, we have T, which is the T times R0, which is 0.330 meters, minus 1.10 Newton meters. That's your total torque. And that is equal to I, which we now know is 0.385 kilograms meter squared times alpha. And I'm going to call this equation 1. Now, we also have a free body diagram for for the other body. So this is the summation forces in the y direction equals mass times acceleration in the y direction. And in this case, what we get is 10.0 newtons minus T is equal to 1.53 kilograms
Ah,
times A. I'm going to call that equation 2. And now, since we assume that it basically the pulley doesn't stretch or the rope doesn't stretch or get slack, so if I pull the rope down 1 inch, then the circumference is going to move by 1 inch. If I do 1 inch in 1 second, then the circumference is going to do the same thing in 1 inch in 1 second. So the velocities would be the same. And if I do 1 inch in 1 second and then 2 inches in the next second, the same thing's going to happen with the circumference, so the accelerations will be the same. Therefore, I can finally say that A is equal to R0 times alpha, or specifically A is equal to 0.330 meters times alpha, and that's going to be equation 3. So if I can solve, for instance, equation 2 for T, that's what I'm going to do.
Professor
Yes.
Younger.
Hmm.
Um, isn't it supposed to be 15 newtons for the weight?
Oh, was it? Yeah, I think you're exactly right. I don't know where I got the 10. Oh, I think I remembered the 10 from the previous thing. Thank you for checking, for getting that. That would have been a major problem.
I'd
So,
make the same mistake. Don't worry.
yeah, appreciate that, guys. It's nice that you're paying attention. Love it. Okay,
But maybe
15.0. Anybody else? Anything else? Anybody sees any problems with?
no, but I was just wondering, since 11 relies entirely on essentially what we got from 10,
Hmm.
what would we do if we didn't already know the moment of inertia ahead of time and we had to find the acceleration?
They can do something like they can say a pulley is made out of a cylinder, and then they're expecting you to use the formula 1/2 mr squared, but they have to give you the radius and the mass, or they would have to physically give you the number.
All right. Uh, I
Does that
was
make
just
sense?
maybe I just remember trying to go over some of the practice questions yesterday, and some of them was like essentially find the acceleration, but they didn't give you the
Ah,
moment of inertia, so it made it a lot harder.
yeah, if you, there's a table that they're expecting you to use, that was the table I showed you as well. And it's a table that appears at the bottom of my test, or at least all my tests after chapter 10. But for instance, there's a formula for a hoop that's just mr squared. There's a formula for a sphere, it's 2/5 mr squared. There's a formula for a cylinder, 1/2 mr squared. They are expecting you to use those. So if you see a
Okay.
drawing and it looks like a cylinder, you can take the liberty of using it as a cylinder.
All right.
Does that make sense?
Yes.
All right. So if I solve equation 2 for tension, what I end up getting is the tension is equal to 15.0 newtons minus 1.53 kilograms times A. I'm going to call this 2 prime, and now I'm going to plug 2 prime into 1. I'm also going to plug in equation 3 into 1. You'll see how I do that in a second. So in place of T in equation 1, I'm going to put 15.0 newtons minus 1.53. I'm going to drop the units for right now because it's getting kind of nasty. So 1.53A All that is just the tension, so I've got to multiply that by 0.330 and then minus 1.10, again, leaving off the units, is equal to 0.385. Now, in the place of alpha, I'm going to take from equation 3 and see that alpha can be written as A over R0. So that's what I'm actually going to use here. In this case, that becomes A divided by 0.330, like that. So now I can simplify by distributing. For instance, 15 newtons times 0.33 should be 4.95. And notice that turns out to be newtons times meters, so I'll go ahead and put the units back in now. The 1.53 was kilograms, 1.53, and that's going to be multiplied by 0.33, and that's meters. So that's 0.5049, and that's kilogram meters. And all of that is times A in that case. Minus 1.10 Newton meters is equal to, now I'm going to take the 0.385 and I'm going to divide it by 0.330, and that's going to give me 1.167. Now that unit turns out to be kilogram meter squared per meter, so that's just kilogram meter. And all of that is times A. So now you can see we have two instances of A, and that's the only unknown. So we're going to pull that 0.5049 to the right and add that to the 1.67. So 0.5049 added to 1.167 gives me, whoa, Nelly, I did. Oh, okay, I see what I did. So 1.167 plus 0.5049 gives me 1.67. That was one extra sig fig there. So 1.672 kilograms meters times A is equal to now 4.95 minus 1.1 gives me 3.85, just like it did before. And that's kilogram, or excuse me, that's Newton meters. And we can see that A, therefore, is equal to 3.85 divided by 1.672, and that gives me 2.303 meters per second is the acceleration. That's the linear acceleration. And that's exactly what the book has. And then we can also use A is equal to R times alpha to get the alpha. So alpha is actually equal to A over R0, which is 2.303 meters per second divided by 0.330 meters. So the alpha is going to be 6.98 or 6.978. And notice that turns out to be just radians per second per second. And that also agrees with the answer the book has. Anybody have any questions on that one? Your book is calling it 6.98. That's what mine rounds to as well. No questions on that? All right, we'll keep chugging along then. That's 1011. We're going to do 1012 now. So example 1012. Oops. And this one says a uniform rod of mass M and length fancy script L can pivot freely, we ignore friction, about a hinge pin attached to the case of a large machine, as in figure 1024. The rod is held horizontally and then released. At the moment of release, when you are no longer exerting a force holding it up, determine A, the angular acceleration of the rod, and B, the linear acceleration of the tip of the rod. Assume the force of gravity acts at the center of mass of the rod as shown. And that's the general rule, by the way. As we're going to start applying Newton's laws of motion to physical objects, then if you since we're actually talking about torque now, the objects are no longer point particles. They have an end, the left end, the right end, the top, a bottom, and the point of application of the force is just as important as what the force is. So when you need to find out the point of application for the weight or the gravity, that's acting at its center of mass. So that's just something we always do. Let me go ahead and draw a little figure to represent the problem we're trying to solve. We have a little pulley, excuse me, a little hinge right here, and attached to that is a rod. The length of that rod is script L, like that, and the mass of that rod is big M. And if we go over to a length L over 2, we get the center of mass, and acting at that point is big mg. Okay. What we're asked to find is the angular acceleration. We want alpha equals question mark, but we also want A, the tip, A, the tip, I shouldn't say final, is equal to question mark. This is another case where we can use a coordinate system whose axis of rotation is right through that pulley. And since it's affixed to a wall or a machine or something, it's not an actual accelerating reference frame. The direction's fixed. So all the stuff that's necessary to apply for Newton's second law in torque form is valid. So we can use that. So we're going to use the summation of the torques is equal to I times alpha. And you can see that the lever arm vector, which really just points from here to the point of application of the force. Now, there's a slight difference. You can see this little difference right here, this itty bitty bit of green that I'm drawing right there. We're ignoring that. We can pretty much assume that maybe it's acting right along here and then the force is acting right along here. I just wanted to point out that I'm sort of ignoring that little discrepancy because I can, and it's not that big of a deal. Okay. But the main thing that we're seeing is that the lever arm vector and the force is acting at 90 degrees. So again, torque is just force times lever arm. So for this case, I get mg times L over 2 is equal to the moment of inertia of a rod rotating about its end. We derived that last time, and what we found was a rod rotating about its end, if it's uniformly distributed mass, has a moment of inertia 1/3 ml squared. So I'm going to put in that 1/3 ml squared for I, and then that is alpha times alpha. Okay. So what we can see from this is one of these L's can cancel out, both of these masses can cancel out, but in fact, what we see is alpha is going to be equal to 3 halves g, oops, 3 halves g over L. So that's the angular acceleration we've got. Anybody have any questions on that part? Now, if we also apply A is equal to R times alpha, in this case, the radius to the tip now is given by A tip is equal to L times alpha. So that's all I need to do to find the acceleration of the tip. I'm going to say A tip is equal to L times alpha. You can see the L in the numerator or in the denominator of alpha is going to cancel out with the L that I have here. So this is going to have to be 3 halves g, and that's the total acceleration of this. Now I want to point.
Is it
Go ahead.
still like that given how it's not how the where it's turning from is in the middle, not like the edge of the wall, since L is like all the way from the wall rather than the hinge point?
Yeah, so in this case, what we're really trying to do is we're assuming, in reality, the rod that we've drawn it has some thickness, but we're assuming it has zero thickness, so that the hinge is right at the corner, which is the same thing as the middle, which is the same thing as the top, which is the same thing as the bottom. So that is sort of cheating a little bit, but that's the way we're treating it.
Okay.
Does that make sense? If we had to
Uh,
do a physical body and it was like a rectangle or something like that, then we would really want to stop and find out what the moment of inertia for a rectangular object rotating about a corner is, and we would have to deal with that. But in this case, I'm just treating the rod as if it's a thin, narrow rod like a broomstick, that's way, way wider than it is, uh, than its diameter is.
okay.
Okay. All right, so that's example 10, 12. I want to point out that notice the acceleration was markedly higher than g. If you ever see someone, for instance, knocking over a smokestack or knocking over a tower or building of any sort, what you'll often see is as the building or the tower starts to fall, it'll often break somewhere in the middle or a little bit higher up from the middle. That's because when you design a structure, you design it to not necessarily accelerate that way. And even if you designed it for wind, for hurricanes or for earthquakes, you're basically just expecting a load that's on the order of 1G, maybe 1G, maybe 1.5G, 2Gs at most, something like that. With that in mind, when you're actually start to accelerate this, since the force of gravity pulls on the center of mass of the tower, the acceleration of the center of mass will be g, but because there's so much more distance up here, a equals r times alpha means that a, since alpha is the same for both the center of mass and for the tip, the a is actually going to be markedly bigger than the acceleration due to gravity, and that's what causes them to break because they're normally not built to withstand more than 1 to 2 Gs. In this case, it came up to 1.5. You could imagine it be even larger for other things. But any questions on that? All right, so now I'm basically I already did what's equivalent to section 10.7. I did like 3 different problems for calculating moments of inertia using integrals and stuff like that. Your book does a couple more, so you can by all means check that out. But I'm skipping that section, uh, not because it's irrelevant, but because I've done what I consider enough. But you should definitely read it over so you'll know about the parallel axis theorem, the derivation of it, the perpendicular axis theorem, the derivation of it. But I'm not going to test you on the perpendicular axis theorem. However, the other examples are certainly fair. So now I'm going to go into talking about the extra little thing that we have to take into account now. As a result of this rotation, we find out that we have a kinetic energy. For instance, if I throw this pin, it has a kinetic energy 1/2 mv squared that represents its center of mass moving at velocity v. But if the thing is not just doing this, but rather is rotating or spinning as it's doing that, then I have a 1/2 mv squared for the center of the mass, but I also have a 1/2 I omega squared for the kinetic energy of the center. So, or excuse me, of the rotation. So now kinetic energy total is equal to 1/2 mv center of mass squared plus 1/2 I omega squared. So that's the new paradigm that we've got to deal with now that we're talking about objects that are not just rotating. If they're just rotating, it'd just be 1/2 I omega squared. But in this case, they're rotating and translating. So it has to be all of that. And of course, I want to remind you that we have our conservation of energy, U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. However, we're starting sort of all over again with conservation of energy because we got a new term. So we're not going to be introducing much of the examples that include a work in, work out, or E loss. So just warning you ahead of time. So let's look at our very first example, which would be example 1015. Example 1015 says flywheels, which are simply large rotating disks, have been suggested as a means of storing energy for solar powered generating systems. Uh, Estimate the kinetic energy that can be stored in an 80,000 kilogram, i.e., 80-ton flywheel with a diameter of 10 meters. Assume it could hold together without flying apart due to internal stresses, even at 100 RPMs. So, what they've given us here is the mass is equal to 80 times 10 to the third kilograms. Notice all the other figures they give us only have like 2 sig figs, so I figured what the heck, there's no reason in trying to say this thing actually has 5 sig figs, so I just called it that way. The diameter, which is twice the radius, is 10.0 underbar meters. Again, making sure I have the 2 sig figs. And we have an omega zero is equal to zero, but omega final is equal to 100 revolutions, REV, per minute. So that's what we're looking at. What we're trying to figure out is if I actually spun this thing up at the full speed of 100 revolutions per minute, how much energy would that entail? And just to see if that's a decent amount of energy or whatever. So the formula we're looking for here is K is equal to 1/2 I omega squared. It's a cylinder, so I is equal to 1/2 mr squared, like that. So now we can go ahead and say K total is equal to 1/2. Now we've got to put 1/2 mr squared and then times omega squared. In order to do that, I really need omega to be in units of radians per second. So omega is equal to 100 revolutions per minute. That means one revolution on the bottom can cancel out the revolution on the top, and that'd be 2 pi radians in the numerator. Similarly, 1 minute on the top can cancel out with the minute in the bottom, but I have to get 60 seconds for that. So basically what we're going to get is 100 times 2 times 3.14159 and then divided by 60, and that gives me 10.47 radians per second as my omega. So now I can put in all the values. This will be 1/4, because a half times a half is 1/4, times the mass, which is 80.0 times 10 to the third kilograms, times r squared, which would be 5.00 meters squared, times 10.47 radians per second quantity squared. So if I go to put all this math in, I can do this 10.47 squared times 80 times 10 to the third times 5 squared times 0.25. And this gives me 5.48 times 10 to the seventh, 1, 2, 3, 4, 5, 6, seventh joules. Uh, this is also on the order of 15 kilowatt hours. So it's really not that much. But the key thing is this is what they asked for. There it is. And to give you some perspective, your book points out that a typical stove, like what you might have in your kitchen, might be 3 kilowatt hours. That would be the power that or the energy that it uses. And if you uh, looked at that, that means that this huge, this is like a 3 story tall, 80-ton object spinning at 100 revolutions per minute. That's a butt ton of energy. 80 tons is like almost as heavy as a tank, a typical tank like the ones we use in our military, for instance, are anywhere from 100 tons to 120 tons of fully loaded Mack trucks on the order of 50 to 70 tons. This is 80 tons, and it's literally 3 stories tall. But still, it only has about 5.48 times 10 to the seventh joules, or about 15 kilowatt hours. So running a stove at 3 kilowatt hours would really only be able to run it for 5 hours. Like you couldn't even cook a turkey because they always take more than 5 hours usually. Any questions on that? All right. So we have another one, another example. This is going to be example 1016. I'm going to go ahead and start another page on this one. So example 1016. This one says a rod of mass M is pivoted on a frictionless hinge at one end as shown. The rod is held at rest horizontally and then released. Determine the angular velocity of the rod when it takes the vertical position and the speed of the rod's tip at this moment. So let me draw a picture of that. This one settles your problem, Colin, with regards to how the center of rotation wasn't exactly lined up. This one has a drawing that looks like it's designed to be exactly lined up. So what I'm going to do just to make sure you can see that is I'll draw a little wall right here. And then I'm going to draw a little uh, pin like this. And we're going to imagine that this rod is so thin that it can fit in this little hinge without getting stopped up. So this rod has a length L like this. It has a center of mass that is over a distance L over 2 like this. It's going to have acting on it a weight mg like that. So we're going to imagine that the rod has a mass m, a length L, so on and so forth. And as it spins, it's going to spin in such a way that it ends up being in this position at the final end. And you can see that now from here to here is L over 2. So if we let this position be y equals 0, then we can use our conservation of energy techniques, and they are U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. Again, we're not uh, dealing with any friction here, so I don't have to worry about work done against friction. I'm not compressing any springs, so basically we can go on the assumption that E loss, work out, and work in is 0. Not only that, we can go on the assumption that the potential energy at the end is 0, so I'm going to put that as 0. And the object starts from rest, so we can say the initial kinetic energy is 0. That leaves us with just the following. We're going to say M times G times L over 2 is the actual potential energy initially. Remember, potential energy is just m times g times y, and you can put the zero of the y anywhere you want. I put the zero of the y L over 2 distance below the horizontal beam because that's where the center of mass will be at the end. Now on the right hand side, this is not translating. This object is just falling like that, right? So it's only rotating about this one end, and that axis is fixed. So it doesn't, I don't have to do the torque through the center of mass because the axis is fixed and the reference frame is not accelerating. So in this case, I'm just going to put 1/2 I omega squared, but we know it's a rod rotated about its center. So I can now say mgl over 2 is equal to 1/2. Now, since it's a rod, I can enter 1/3 ml squared, and then that's times omega squared. You might notice that L squared omega squared is actually v squared. So that's the velocity of the tip. So we can put that there as well. That'll allow us to do it. Notice there's a common factor of 1/2 on both sides, so I can get rid of that. There's also a common factor of m on both sides, so I can get rid of that. And there's a common L on both sides, so I can get rid of one of those. And what I get is the final angular speed, omega, is going to be equal to 3g, that's the 3 from the denominator, and then that will be divided by L, and then I have to take the square root, so it's 3g over L is the actual angular acceleration. And if I use v tip is equal to r times omega, in this case what we're going to get is v tip is equal to L, which is the real radius that we're doing for the end of it. So that's going to be L times the square root of 3g over L. If I pull the L inside, that becomes L squared. So I get 3g L squared over L. And therefore, I can find that V tip is going to be actually the square root of 3GL. Any questions on that? Notice if you dropped an object and just allowed it to fall straight down, we know from kinematics as well as from conservation of energy that its velocity it would have after reaching a height of L over 2 would just be the square root of 2g times L over 2, which would just be g times L. In this case, we actually got 3g times L, but it's going in an entirely different direction and entirely different motion. But anyways, that hopefully that just points out to you how much different rotational motion is than translational motion. Let's go on to our next example where we're now going to apply Newton's laws of motion. And in so doing that, we're going to use it to figure out things like what would be the speed of a sphere rolling down an incline. We're going to work that out with conservation of energy first, though. So let me do that. I'm going to draw a line here. And this is going to be example example 1017. Somebody just came in. Let's let them in. Okay. So what we're looking at here is a sphere, uniform solid sphere. It's got a radius R0 and a mass big M. It's sitting on top of an inclined plane, and the height is h. And the angle right here is theta. That might come in handy later. The main thing is we're going to use conservation of energy, and what we want to figure out is what will be the speed of the center of mass at the bottom? So down here, it has a V center of mass, and that's what we want to work on. So what I'm going to do is again take my U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. We're going to have a lot of reductions like we always do. The initial potential energy is going to be M times G times H plus R0. The initial kinetic energy is going to be 0. The work in is going to be 0. The work out is going to be 0. The E loss is going to be 0. In this case, the potential energy is not going to be 0 at the final end. It's going to be mg times R0. And then we're going to have plus. In this case, we have translational motion. The center of mass is moving, but we also have rotational motion. So we have to add both terms. This is going to be 1 half m v center of mass squared plus 1 half I omega squared, like that. We do know it's a sphere, so I is equal to 2/5 mr squared, and that'd be R0. So I can plug that in, and we'll get mgh plus mgr0 equals mgr0 plus 1 half mv center of mass squared plus 1 half times 2/5 would be 1/5 m r0 squared omega squared. But notice r0 times omega is just v center of mass. So that's going to come in handy. Not only that, we have a common factor of m that can be taken out, and we've got a mgr0 on both sides, so we can get rid of that. Now we're left with G times H is equal to 1 half V center of mass squared plus 1/5 V center of mass squared, which is obviously 7/10 V center of mass squared. So we can go ahead and say that the V center of mass is actually equal to the square root of 10/7 GH. Again, if you dropped an object, its velocity, if you started from rest, its velocity would be the square root of 2GH. In this case, we get 10/7, which is almost 2, but not quite. But that's because some of the energy is going into a rotational motion and some's going into translational. You can sort of think of it that way. But anybody have any questions on that?
No, but please give me a second. That was a lot of numbers to write down.
It's a lot of stuff, right? One thing I'll tell you guys about this is the next example. I'm going to skip it because we're running out of time, but it's one where they're asking you about letting a block slide down without friction, letting a solid sphere roll down, let a solid cylinder roll down, let a hoop roll down, let an empty soup can roll down, and find out which one goes the fastest. You can see from this that it's basically going to be the same answer every time you do it. Specifically, the velocity of the center of mass is going to be equal to a square root of g h over whatever that multiplier is in your moment of inertia formula. Like, for instance, for a sphere, it's 2/5, and for a cylinder, it's 1 half. So that's what would go in these parentheses, and then there's a plus 1 here. So the main thing that you see is the larger this number from in front of the center of mass is, then the smaller the velocity will be, and therefore the later it will hit the bottom.
I wrote that down, but I'm trying to read. What is the word for the fifth of m where you have like the r squared times omega squared? Is that ym or what is
That's
that?
V center of mass. It's a V with a
Oh,
subscript center of mass. Yeah, it
okay.
doesn't look that good.
All right, and I got that down. Thank you.
No problem. All right, so let's move on. The main thing is, like I said, that conceptual example, 1018. From this, you can see whatever the multiplier is in front of mr squared, the bigger that is, the smaller the velocity will be, and the smaller the velocity will be means the later it'll get to the bottom. So the frictionless block sliding down the incline will get first, then the sphere, then the solid cylinder, then the empty can, and then the hoop. So that's the main thing that we're looking at. I'm going to skip on this and move on to example 1019. And this is really the last one I'm planning on doing anyways. It says analyze the rolling sphere from example 1017 in terms of forces and torques and determine the velocity VCM of the sphere's center of mass at the base of the incline and the magnitude of the friction force. So we want VCM equals question mark, and I'll put an F on that for final. And we also want to know the friction force question mark. Okay. Now, what we have here is the same sort of inclined plane. And what I'm going to say is this distance right here, parallel to the incline, is going to be L. I'm going to say this distance from here to here is H, and this angle is theta. And that's because I know what's going to happen, and I'm going to need to find a symbol for the whole length down there, because what I have to do is use a kinematic equation to figure out, once I have the acceleration, exactly how fast will the ball be going by the time it gets to the end of the incline. So we're starting it right here, like that. It still has a radius r0 and so on and so forth like we had before. It still has a mass m. What I want to do though is I now need to draw the sphere so we can have a basically a free body diagram of this that is helpful. So I got to do a free body diagram for this. To that end, I'm going to draw a circle right here roughly. Okay. The inclined plane is going to be going by like this, something like that. And I moved it down a little bit. Now, what's really going to happen is we're going to set up a coordinate system that looks like it should be roughly, that's my x-axis going parallel to the incline. Something like that. That looks fairly parallel. And this will be my y-axis. That's my x-axis. Now, what we have here is the weight, mg, acting downward. That can be broken up into a, because this angle right here is theta. This angle right here is also going to be theta. Hopefully I'll remember that from previously. And this side right here is going to be the force parallel to the incline. This one, on the other hand, is going to be mg cosine theta, and this one's going to be mg sine theta. Now, in addition to that, we're going to have a friction force, which acts right here along this direction. And we're also going to have a normal force that goes that way. So now I'm going to say the summation of the forces in the x direction equals mass times acceleration in the x direction. And from that, I'm going to get mg sine theta minus the friction force is equal to m times a. I'm going to call that equation 1. Now the summation forces in the y direction equals mass times acceleration in the y direction. This is an object rolling down an incline though, so there shouldn't be any acceleration in the y direction since the y direction is literally perpendicular to the incline. So in this case, we're going to get F normal minus mg cosine theta is equal to 0. That's going to give us that the normal force is equal to mg cosine theta, which we can call that equation 2, but really not going to need it. Now I'm also going to do the summation of the torques is equal to I times alpha. In this case, we actually have the objects rolling down the incline. So that's an accelerating reference frame. So we're forced to do the torque about the center of mass, which is the center of the sphere. And that's kind of nice because using the center of the sphere, we only have one torque acting on it because the mg cosine theta and mg sine theta are both technically acting at the center of mass and therefore have no lever arm. And the same thing is true with the normal force. So in this case, all I'm going to have is the friction force, which is acting perpendicular to the radial line. So that's the friction force times R0 is equal to the moment of inertia, which is a sphere. So that'd be 2/5 mR0 squared times alpha, like that. That's going to be equation 3. And if we assume rolling without slipping, then we also have A is equal to R0 times alpha, and that'll be equation 4. So what I can do is I can solve 3. So I'm going to solve 3 for F and plug it and 4 into equation 1. So you can see from equation 3, this R is going to cancel out with that R, and we're basically just going to get F is equal to 2/5 mR0 alpha. So I can just put that in, and that's going to be mg sine theta minus 2/5 mR0 alpha is equal to MA. Now, I'd like to solve for A first, so I'm going to go ahead and replace alpha, or this R0, if you will. I'm going to replace the R0 alpha with just A. So now we can see that mg sine theta minus 2/5 MA is equal to MA. Now you can see that the masses are all canceling out, and what we have is G sine theta is equal to 5/5 plus 2/5, which is 7/5 MA. So A is actually going to be equal to, oh, the mass was supposed to cancel out. Sorry, I left that out. So that's supposed to be 7/5 A. So A is supposed to be equal to 5/7 G sine theta, which isn't necessarily that helpful yet, but we can figure that out because we're supposed to ultimately find what the center of mass velocity is. And in order to do that, I need to know what the acceleration will be. Now, I can take that the sine theta is actually equal to opposite over hypotenuse, so that's going to be h over L. So now I've got 5/7 G times h over L, because that's what the sine is. Now I can also say that v squared is equal to v0 squared plus 2a x minus x0, but the x0, x minus x0 here is the total distance traveled, so that's going to be L, and the initial velocity is 0, so I can figure out that the actual final velocity, V, would be the square root of 2A, sorry, I wrote G there, 2A times L. So that's the velocity of the center of mass, final. So now I can say the velocity of the center of the mass, final, is equal to the square root of 2. Now I'm going to put in my value of G, or excuse me, my value of A, which is 5/7 G H over L. And then that's times the L that's already in there. And lo and behold, we get exactly the same result that we had before, specifically the square root of 10/7 GH. This is one of the first things that made me fall in love with physics is an entirely different scenario. Notice we worked this all energy methods and we got this value for the final velocity. Entirely different way, we got exactly the same velocity. Isn't that awesome? Now, the last part of this is now that we have the alpha or the A, we can actually figure out what the friction force is. So the friction force is going to be 2/5 M R0 alpha, which is 2/5 M times A, which is 2/5 M times 5/7 G H over L. Now you can see that the fives cancel out and I get a friction force equal to 2/7 mg times H over L, which is just the same thing as sine theta. So that's our friction force. Anybody have any questions on that one? All right, so we managed to work this out and we discovered that in fact we got exactly the same results. And we also found that we can get the friction that's exactly what the book said as well. So that all looks good. The rest is just quote unquote more advanced examples. They're really good. I don't think there's any need for us to cover them. I mean, you can certainly look them over, and it's not like I'm saying this section is you're allowed to omit it or anything. That's not what I'm saying at all. I'm just saying I've done what I believe is an ample number of example problems for this chapter, so we can move on. Uh, we're going to cover chapter 11 next time, and I guess I'll go ahead and let you go. We have around 10 minutes left, 13 minutes left. Actually, let me go ahead and start into chapter 11. That's what I'll do. Anybody have any questions before I start this?
Yes, but it's about like a specific problem we haven't covered tonight, so I'll ask you after class.
Okay. Actually, that'd be fine because I don't necessarily want to jump into chapter 11 yet. So if you want to throw that up there,
Uh,
everybody's welcome to split if you'd like. Just make sure you chat at me your first and last names before you go. But let me see what I can do with him. And this will be all recorded anyway. So even if you miss something good, it'll come up on the video when I post it.
um, in that case, I was trying to do a get excel yesterday do a problem for excel to find the rotational acceleration
Mm-hmm.
of a bar that was like pushed on the east side uh, uh, southward by 200 newtons and north side or west yeah, one side was being pushed up by 200, the other side was being pushed down by 200 newtons. I was trying to find out what the rotation acceleration was.
I gotcha. So you had something, you said it was a bar.
Yeah.
So you can say like maybe you had a rod like this
Yes.
and you had a force of like 200 newtons.
Yeah, the west side was being pushed up by 200, the east side was down by 200, and it was 5 kilograms and 2 meters long. I thought I had it right, but when I put in the answer, it said it was wrong, so I didn't know where I went wrong.
Gotcha. And they said the length is 2 meters,
Yes.
and they're asking you for the angular acceleration or for the linear acceleration, or well, I guess
The
it's
angular acceleration.
okay. So what we have here is the summation of the torques is equal to I times alpha. And in this case, we're going to assume it's a uniform rod, so everything's going to rotate about the center of mass like that. So in this case, what we're going to get is a 200 newtons times 1.00 meters. Notice that force is actually perpendicular to that lever arm. I'm sort of ignoring the vertical thickness of the rod again. Similarly, we have a lever arm over here that's also 2 meters, but again, that's at a 90-degree angle. Both of these are tending to produce a clockwise rotation, which for the heck of it, I'm just calling positive because might as well. So now I've got plus 200 newtons times 1.00 meters. And then all of this is equal to, now this part could have been what you did, but when you rotate this about the center of mass, it's 1/12 ml squared. So I
Okay,
don't,
yeah, that I definitely didn't have that part there. It's like I couldn't
yeah.
find anything about 1/12 there, so I was like, that would definitely wasn't something I
Yeah,
could.
that was what I derived in class last time. We did it once with this parallel axis theorem, but we also did it with the integration techniques. I was afraid that might have been what was happening. So I'll just say right here, this is going to equal 1/12 times the mass, which is 5.00 kilograms, times the radius, which is 2.00 meters squared. And then all of this is times the alpha. So actually, I don't even need to put parentheses there. I'll just say times alpha. So 2 times 1 plus 2 times 1, that's 2 or 200 plus 200. So this is 400 Newton meters is equal to, now I'm going to say 500, or excuse me, 5 times 2 squared. And then I'm going to say divided by 12. So this
And
is
is
1.6. Go ahead.
I was gonna say it's just 5/6, right?
Mm-hmm.
No, wait. That's wait.
Yeah, well, actually 5/3
What? Why is
because
it?
the 2 is squared. Don't forget that.
But it's 1/12. Then you have a 5 times. Oh, I didn't see this the square thing on the
Yeah,
thing. Okay.
exactly. So that times alpha. So this is going to give us alpha is equal to 400 Newton meters divided by that quantity. That gives me 240 radians per second per second.
Okay. I believe that was one of the answers on there. I didn't get that there. Why is it 1/12? What example showed us it was 1/12 again? 'Cause I went back
Uh,
through all the examples. I couldn't find anything for this one in particular, just because it was like with the two things acting on the rod at the same time.
Uh, the rule is if we want to do the parallel axis theorem, then the moment of inertia through a parallel axis is equal to the moment of inertia through the center of mass plus m times d squared, where d is the distance between the center of mass and the new rotational axis. So if you
Okay.
wanted to do this, you'd take the 1/3, which I think you were comfortable with already, right?
I think so, yeah.
Yeah, that's what we did when we did around the ends. So now what I'm going to do is since I'm going around the end, uh, I'm a distance of L over 2 from the end, so I square that. This gives me 1/3 ml squared plus 1/4 ml squared. That, of course, is 4/12 plus 3 twelfths ml squared. And of course, the sum of those two, wait a second, 1/3 ml squared. Oops, no, I did it backwards. Sorry about that. I was thinking this math is not working right. The This is right, but the center of mass is the one we're solving for. Sorry about that. So in this case, what we do is 1/3 was what we had around the end, and then the I center of mass was the one that we're looking at. That's the one we're trying to find. But we know the axes of rotation differ by a distance of L over 2. So this is going to be mL over 2 squared. So we get 1/3 mL squared equals I about the center of mass plus 1/4 mL squared. Now you can see that this would be 4/12 mL squared minus 3/12 mL squared is equal to I center of mass, and therefore you get 1/12 mL squared is equal to
All
the
right.
I center of mass. Does that make sense?
Yes. Is it always that for when you're um um just because it's I'm doing my best to follow along.
Yeah,
Is it
for a
always that
thin
when it's
rod.
yeah,
Yeah,
for
for
the
a thin
for
rod
a
that's
rod with two
uniformly
forces,
distributed.
it's always the 1/12th, or is it just for this in particular?
No, it's just for a thin rod, and by thin we mean one, it's uniformly distributed. So if you cut out a 1 centimeter segment of this rod and you cut out another random 1 centimeter segment, they better weigh exactly the same. If you have that, then you have uniformly distributed mass. And the other thing is the radius has to be small compared to the length. And long as you have radius slash diameter, long as you have that, then automatically the moment of inertia about the end is 1/3 ml squared, and about the middle is 1/12 ml squared.
Okay. All right. Yeah, I think that was why um I kept trying to find the inertia or the moment of impact yesterday, but
Right.
or moment of inertia yesterday was like a lot of it got complicated when I looked in the book. It was like, yeah.
Gotcha. Here's the
Okay.
derivation I did last time if you want to see that. Uh, that's one way you can get the 1/12 ml squared. You can see it in this part right here is when I did it the long brute force way. This is when I did it with the parallel axis theorem, that and this.
All
And
right.
then this is just for the end. So that was in the notes from last time, if that helps you.
Yeah, I recognize where I wrote that down. Okay. One other thing before I go
Hmm.
is um one of the answers yesterday I was going through and um I put in it was essentially kilogram it was essentially asking crap, what was it? I wrote these down to help me study. Force multiplied by time. I wrote momentum and it told me I was wrong. It was impulse, but isn't impulse and momentum roughly the same thing?
It is, but there's a little nuance. The impulse is the change in momentum. So that's if you said delta p, they might have accepted that, but if you say momentum, it's not technically correct to say it. The F delta t is just the delta p, and that
All
comes
right.
from the idea of basically F is equal to delta p over delta t.
At that point, it feels like semantics, but okay.
Yeah, it is a little, but it's conceptually it's an important thing. You don't want to randomly say, "Hey, the impulse is the same as the momentum," because you would actually come up with a force that would be zero when the momentum is zero, and that's not necessarily the case.
All right. All right. Thank you.
No problem. Anybody have any other questions? Well, you folks are free to go. I did correct that practice test, so you go ahead and knock that out. At least take it once, even if you got a 60 out of 60 or whatever the short number of points were. That's fine, long as you've got it. I'll make sure that you get 100 for that. But the key point is, I need you to do it so you can get some experience with those other chapters, other than just the I think it was 9 and 10 that was on there. So please do that. Uh, you're welcome, Zach. I appreciate you coming. And appreciate you
Thank
coming,
you.
Ryan,
Have
as
a good
well.
night.
You too. Thank you. And that looks like it. So that's everybody. Have a good evening. Bye bye.